All right. Thank you everyone for joining us today for our first webinar. My name is Eric Wolfram. I'm the laboratory manager of the Riverbank Acoustical Laboratories. Many of you I've met before and have even done testing with us. This presentation will be recorded, and there will be a recording available on our website in the future, and also a PDF, I believe, will come to you as well. If you have any questions during the talk, there is a questions bar on the GoToWebinar bar. Type it in there. The chat or the presentation has all attendees muted. So throw your questions in the chat, and then Becca will stop me and read them as we go. At the end, there is also the final slide will have my email address, and feel free to reach out to me if you'd like to ask a question in private as well. All right, so the purpose of this webinar is to give an overview of the process for testing sound absorption of spaced objects, which could include the classic acoustic baffles or acoustic light fixtures or other felt object arrays. Basically how we approach testing those, what the results mean, and ultimately how you can use them both for predicting the absorption of or the reverberation time of a particular space, and also how to market these products. So before we start, just a note on units, because this can be a little bit confusing the way the North American labs handle units. So ASTM requires all of our testing to be performed and documented and reported in the International System of Units, or SI. So that's meters, kilograms, and the unit of sound absorption, as it's defined in C423, sound absorption in meters squared. However, we know that in the United States, most of the architecture industry hangs on to this inch-pound system, which is feet, inches, pounds, and Sabins of sound absorption. So for this talk, we will mostly focus on using this inch-pound system of units. However, note that ASTM defines things in meters squared, and there may be a couple places where we bounce back and forth. Just a quick conversion, one Sabin, which we'll define later, one Sabin is equal to about 0.0929 of sound absorption area, meters squared, which is also the conversion of 1 square foot to 1 square meter. So meter squared of sound absorption is also sometimes called a metric Sabin. These two terms are used at different places in the ASTM standards, and this metric Sabin term may make a return. One thing to watch out for when you look at sound absorption test results is that the sound absorption area meters squared, or the metric Sabins, look like sound absorption coefficients because they tend to fall in that same range of less than 1, like 0.885 or something like that, but they're not the same thing, and we'll talk about that more later. So first, what is reverberation? And reverberation is the property of a space that we're most concerned with when we talk about things like NRC, sound absorption coefficients, or Sabins, and it's the property of these spaces that we are trying to treat by installing sound absorption materials. So the definition of it is that the sound in an enclosed space that has been reflected repeatedly or continuously within the boundaries of the space, we measure it in terms of the reverberation time, meaning the amount of time it takes for sound to decay 60 decibels after the source has stopped. So this drawing here is not exactly accurate to how sound truly behaves, but it's a really good starting place for us. So this would not be reverberation. They're illustrating a single reflection where sound comes from the source and bounces off a hard wall. But in truth, in any room, sound will disperse more widely than this and will reflect off of all the surfaces around the room more at many different angles, and then multiple times. So you'll have first order reflection that bounces back, and then it will reflect off the ceiling, a second order, third order. And as it's continuously dispersing, there isn't an array of sound, it becomes a chaotic sound field, or ideally chaotic. In some spaces, it's you'll have modal characteristics, which we won't get into today. We're going to show you a demonstration, an audio demonstration. Just a note, these will be more effective with headphones, but it will work on loudspeakers as well. So this first recording will show it's a toy pop gun from the 1950s that produces an impulsive sound. The first example here was recorded in our engineering space, which is lined with sound absorbing materials. This isn't a true anechoic chamber, but it's a space we use for determining frequency response out of equipment, that sort of thing. In that first sound, you heard an impulsive pop, and you even heard the detail of the mechanism, the detail in the metal in the gun moving. In this second example, we have recorded it in the diffuse field reverberation chamber of room 0. So this is our main test chamber. It's a very reverberant environment. So that is a space with very little sound absorption, where all the walls are essentially reflective for sound. And it's a big difference. That was the same source. That was the exact same pop gun in just an exact opposite type of environment. Same recording device, same sound source. Next, we have that same sound source, that same pop, recorded in what I would consider to be a well-controlled acoustic environment. This is actually my office, which has classic suspended acoustical ceiling tile, and I have some other foam panels and things like that at various places. So there you hear the room, you hear the environment that it was recorded in, but it's not at all intrusive. Some people might say that it's actually helpful. It gives a sense for the space. It gives a sense for the environment. To have recordings made in spaces that are not too acoustically dead. And so this would be an example of a good space. The fourth sound is recorded in an office environment that has too little sound absorption. So this is maybe a real room, and some of you know this space. This is our client lounge, which famously we took out the ceiling tile. So we do the thing we complain about architects doing. We took out all the ceiling tile to give it that exposed look, but we have not yet put sound absorbing material in, which we will someday. So here, there's a lot more response from the room. It almost has that sort of, should I say, the bathroom sort of quality to it. It's a little bit less pleasant to be in. And it can interfere with things like speech intelligibility, which I'll demonstrate next. So what we have here are 4 recordings of a quote from Wallace Sabin from 1900 on reverberation, or his estimation of what makes for a good acoustical environment. The first will be recorded in our diffuse field reverberation chamber.
In order that hearing may be good in any auditorium, it is necessary that the sound should be sufficiently loud, that the simultaneous components of a complex sound should maintain their proper relative intensities, and that the successive sounds in rapidly moving articulation, either of speech or music, should be clear and distinct, free from each other and from extraneous noises. These three are the necessary, as they are the entirely sufficient, conditions for good hearing.
So, as you can hear, the speech is incredibly muddled. It's difficult to make out what I'm saying. You would not want to do something like a video call there. You would not want to have a meeting in that space. And actually, people who have some hearing loss are going to have an even harder time understanding what's being said in that room, because your brain loses the ability to differentiate those sounds as you lose sensitivity in hearing. So it's very disruptive to the function of the space if that space was an office, for example. And if you have a very large office or a meeting space, and you have all hard surfaces in the room, it will sound like that. And I've heard examples of that. So the only function that might actually work well in that space would be something like Gregorian chant, but I doubt that's what they're doing in the office. So the second example is that same recording that same reading, same microphone, recorded in our engineering space, our soft room, a highly absorptive space, which is almost like an anechoic chamber. In order that hearing may be good in any auditorium, it is necessary that the sound should be sufficiently loud, that the simultaneous components of a complex sound should maintain their proper relative intensities, and that the successive sounds in rapidly moving articulation, either of speech or music, should be clear and distinct, free from each other and from extraneous noises. These three are the necessary, as they are the entirely sufficient, conditions for good hearing. So there we have the same person speaking, the same text, the same microphone at the same distance. The only difference is the room it was recorded in. That's closer to a broadcast recording studio where they don't want any response from the room at all. You don't need to go that far with it to get a good environment for your office or any other general use space, but that shows you just how dramatic the room itself, just how dramatic that difference can be. This recording number 3 was made in our office, our client lounge, which is probably a little bit too much reverberation, but not as extreme as the reverb chamber. In order that hearing may be good in any auditorium, it is necessary that the sound should be sufficiently loud, that the simultaneous components of a complex sound should maintain their proper relative intensities, and that the successive sounds in rapid moving articulation, either of speech or music, should be clear and distinct, free from each other and from extraneous noises. These three are the necessary, as they are the entirely sufficient, conditions for good hearing. So there you see, you may have not had a problem understanding the speech, understanding the words, but frankly it sounded like it was recorded in a bathroom, right? It was not sonically pleasing. So that's a case where that room needs more absorption. It needs something like suspended baffles or sound absorbing materials installed in the room to get it to something like this speech recording number 4, which I would call a well-controlled office environment. This is maybe closer to what it should sound like. In order that hearing may be good in any auditorium, it is necessary that the sound should be sufficiently loud, that the simultaneous components of a complex sound should maintain their proper relative intensities, and that the successive sounds in rapidly moving articulation, either of speech or music, should be clear and distinct, free from each other and from extraneous noises. These three are the necessary, as they are the entirely sufficient, conditions for good hearing. So there you hear the response of the room, but it's not in the way of the function of the space of the recording. And that's a good target, what you're looking for when you treat a space with sound absorption. This fifth recording, I'm putting out as maybe an example of a space that's not perfect, but not terrible. And the truth is that there is quite a wide range of acceptable reverb times for a general purpose space. So, spaces that are used as meetings or gathering spaces where speech is occurring, but it's not a critical listening space. So, meeting spaces, halls, offices, that sort of thing. I believe they have a wide acceptable range, and then where you get complaints is when you're way outside of the target. However, a space like an auditorium or music performance hall, concert hall, movie theater, these spaces where sound is the critical function, especially amplified sound or music, there you have to design the space to very specific conditions based on that function, based on the space, and that is the work of an acoustical consultant. So any critical listening space, we'd recommend using a consultant. But here's your example of marginal or okay. In order that hearing may be good in any auditorium, it is necessary that the sound should be sufficiently loud, that the simultaneous components of a complex sound should maintain their proper relative intensities, and that the successive sounds in rapidly moving articulation, either of speech or music, should be clear or distinct, free from each other and from extraneous noises. These three are the necessary, as they are the entirely sufficient, conditions for good hearing. So there you hear the room a little bit more than you'd like to, but it's not in the way. All right, this may be a good place, Becca, for any questions if you have any.
Yes, we actually do have one. Does the angle of incidence have an effect on the decibel level of the reflection?
Oh, yes, definitely. And that can be, so ideally when we're talking about reverberation, the angle of incidence is not as critical, assuming that sound is diffuse in the space, which is what we try for when we design reverberation chambers. But in practice, in most listening environments, you have these, they call them specular reflections. So problematic single reflections. A very common example is an auditorium where you have the loudspeakers maybe above the podium, and they're projected at the audience, but they also are projected at that back wall. And you get a slap off the back wall, which is a single reflection, which comes back at a specific delay from the source. And that can be a big problem. And you, as an acoustician, will know that, and they will want you to treat that single wall with sound or with sound absorbing materials to prevent that single reflection. It's a related problem to the sound absorption and the reverberation time problem. It's related, but it's something that also has to be considered separately. So yeah, you can have single reflections based on the geometry where you have a problem. This example in this diagram here is really trying to demonstrate like a slapback echo. So we talked about reverberation. We know what it is. Well, how can we predict it? And this gentleman, Wallace Clement Sabin, in early 1900s, started the entire field of architectural acoustics, or the science of architectural acoustics, by dropping this equation, which is essentially like the E equals MC squared of acoustics, of architectural acoustics, where he's given us a tool to predict the reverb time based on the volume of the space and the total sound absorption, or the Sabins, present in the space. So what is a Sabin? What is this unit of sound absorption? It's actually a debated topic. So the true definition is, this is the definition of a Sabin, and it's a unit of sound absorption defined by this equation. But approximately, it has been compared to 1 square foot of perfectly absorbing surface. It may have been intended that at the time, that's what was intended with that, is, 1 Sabin is equal to 1 square foot of perfectly absorbing surface. So by that, what we mean is, just as shown in this photo here, there's an area of the wall that is hard, and light reflects off of it, and you can see that part of the wall. And there's an area of the wall with a hole where light does not reflect out of it, and all the light that goes in, none of it reflects back. So similarly to sound, we have areas where sound will reflect back and areas where sound will be absorbed. The physics of it, the sound encounters a material, there's friction as it flows through the material, and it loses energy to heat. But a good way to think of it is, an equivalent area of perfect black where no light is reflected is like a Sabin, is an area of sound absorption where no sound is reflected. The difference between light and sound in this example is light has a much smaller wavelength. So what's a big hole to light could be a small hole to sound. So that's a whole aside. But that's essentially what a Sabin is. It's an equivalent area of 1 square foot of sound absorption. I think there's a lot of old references that might describe it as 1 square foot of open window. But again, that's more of like an analogy or metaphor than what its actual definition is. So we have a problem in the modern office design, and many of you are aware of this. So this, I don't know, I did an internship when I was in high school at a .com company, and this is exactly what the office was like, and I can still remember hearing it. I could still hear this space just by looking at this photo, even though I've never been in this particular office. But acoustically, this worked great. You have a sound-absorbing ceiling, sound-absorbing cubicle partitions, carpet, but visually, this is not the aesthetic that they want to go for today. This is the aesthetic that architects and designers are looking for, at least in the 2010s. Who knows what's on the horizon? But this hard, smooth, clean, open look. The problem you can already anticipate is there is nothing to absorb sound in this space. And I can hear this space as well, and it sounds like my reverb chamber. So imagine, trying to have phone calls, conversations in here, and there's just that echo, and the reverberation, which also tends to make sources in the room sound closer together and more annoying to each other. The sound sounds like it's everywhere. That's where many of you come in, as you have products that are intended to be installed in environments like this, where they can solve this problem. They can solve this reverb chamber problem. And we have a test method, which goes back a very, very long time, to determine the sound absorption of these different products and materials. And how this works is, we use a variation of the Wallace-Sabin equation. This equation is defined by ASTM C423. So it's an international test standard. And this equation allows us to determine the total Sabins in the room based on the volume of the reverb chamber and the measurements of the decay rate in the chamber and the temperature but of the air for speed of sound. So if we measure the sound absorption in an empty reverb chamber, we can get the total Sabins for the empty chamber. Then we install a test sample. We make those same exact measurements, again, with that only single variable change. We have a second sound absorption area after the specimen has been installed. And the difference between those two, we can attribute to the sample. So we could say this sample added 50 Sabins to the room. And that's equivalent area. So that's essentially adding this, let's say it added 50 Sabins. That's like adding 50 square feet of sound absorption to the room. For many of the traditional products and systems that have been tested, they're flat, planar surfaces. Think sound-absorbing wall panels, acoustical ceiling tile. They're essentially a flat wall or ceiling mounted material. In this case, we would all agree, I would say, I think all reasonable people will agree that if this is an 8-foot by 9-foot area of material, that there are 72 square feet of material here. So if we have our total absorption provided by this test sample, and let's say it was 72 Sabins, and we agree on the area of the sample, we can take that total added absorption and divide it by that area, and we get something called the sound absorption coefficient. This term, absorption coefficient, from a physics standpoint, may be used incorrectly, but it's a real useful term. It's a real useful analogy. So if we had 72 Sabins, or 72 square feet of absorption area from 72 square feet of sample area, then we have an absorption coefficient of 1.0. And these measurements are made at every frequency band across the spectrum. So it would be a little bit cumbersome for product manufacturers to market their materials with sound absorption coefficient of 0.75 at 250 hertz, 0.8 at 500, basically reporting a spectrum of absorption. So ASTM has given us this single number rating called the noise reduction coefficient, or NRC. Many of you know this. This is, if you're a product manufacturer, this is usually the rating you're being asked for. What's your NRC? What's your NRC? It's a historical rating to kind of turn that spectrum of the performance into a single number. The definition of it is it's the 4 1/3 octave bands at 250, 500, 1000, and 2000 hertz, rounded to the nearest 0.05. So it's sort of a 4-frequency average. It's kind of gives a good sense for the average performance across the spectrum. So for example, something like this 2-inch thick fiberglass panel may get something like a 1.0 or 1.05 sound absorption, NRC rating. NRC is actually not the current defined term by ASTM C423. It has been replaced by SAA. However, the industry still uses NRC, so Riverbank provides both. We provide NRC and NRC ratings for any two-dimensional installation of material. Just a little sidetrack here. Why is SAA better than NRC? So NRC uses a more limited frequency range. It doesn't consider absorption below 250 hertz. It uses only these 4 1/3 octave bands, which this is probably the most surprising thing to acousticians. In fact, many assume that it uses more than that, because how could it only use those 4 1/3 octave bands? But that's how it's defined, or was defined. So, and then this rounding to 0.05, many of you who do a lot of testing encounter this problem. Historically, I think the way they thought of this is they didn't want to overstate their precision. However, so they would round it to 0.05 to not overstate precision and claim we could measure absorption to 0.01. But the problem is that introduces error, which some cases can expand the difference of two very similarly performing materials. So this example here, you have two different materials that are virtually identical, but are showing up as a 0.65 and a 0.7. The name is problematic. So noise reduction is a term we define elsewhere at ASTM for essentially transmission loss, uncorrected transmission loss. So the name is misleading. It doesn't actually measure the ability of the product to reduce noise level precisely. That there is a relationship, but it's not exactly what we're measuring or reporting. So,
Eric,
yes.
we have a couple questions.
Sure. Perfect timing.
First one is, why do I so often encounter acoustic products like baffles that give absorption coefficients above 1.0? Shouldn't 1.0 be the theoretical maximum?
Okay, good question. So we'll get to baffles because that's a whole thing the whole other can of worms that we haven't gotten into yet. Because with baffles, we don't all agree on what the area is. But even in this example, this product here, I don't know if it's a product, this material gets NRC 1.05, so repeatedly. So that should be impossible, right? Because that means you have more absorption area than you do sample area. And that's why I come back to this term, absorption coefficient, is not used correctly from a physics perspective. It's not exactly what it is. And part of, so the causes of this can be, one, this equation may not be finding exactly what they thought it was in terms of square feet of perfect absorption, but we all agree on the unit of Sabin and how it's defined. We just don't agree on what it means, if that makes sense. So, or what it really is. So, but it's close to 1 square foot of perfect absorption. So even if we had no edges or no other boundaries, but a perfectly infinitely absorbing material, you would still get more Sabins than you have square feet. Another part to this is it's commonly referred to as edge effects, but I've yet to hear a good physics explanation for it or a way to quantify or predict it, although there are a number of people working on that. But there's something happening around the boundary of the sample where sound waves that are relatively large relative to this sample and this boundary, they're not cut cleanly at this boundary. There's some fuzziness that happens, and you may get a little excess absorption around the perimeter. And so that's sort of reinforced by the fact that the more perimeter to area ratio you have, the more problematic those edge effects become, the more they bias the results. So, I mean, ideally, every sample would be perfectly circular or infinite, but that causes other practical challenges for the testing. So the fact is, one, it's not alarming when absorption coefficients go over 1 or NRC goes over 1 when they're properly tested and reported. That can happen. It's not alarming. And then 2, with baffles, for example, you may be seeing things like 1.3 NRC, 1.6 NRC. That's because the area value that's used to calculate that is probably applied incorrectly or is not used the way ASTM defines that it should be used. Coefficients and NRC should only be applied to flat treatments. They are not applicable to suspended objects. And we'll get to that. That's the next step. Any other questions?
Yeah, can you give a little more detail on what a 1/3 octave band is?
Yes. I'm gonna go way forward here. Sorry, we're gonna ruin this. We're gonna spoil the surprise. But the measurements are made across the range of hearing. So humans can hear ideally from 20 hertz to 20,000 hertz. And hertz is the measure of frequency, which is the speed at which the variations in air pressure are fluctuating. So faster fluctuations we perceive as higher pitch. Slower fluctuations we perceive as lower pitch. Those slower fluctuations also have a longer wave. So 1/3 octave bands are a way to slice up this continuous spectrum of frequencies and wavelengths that we hear into a manageable slice. And we use something called octave bands, which is where you see the distance between 500 and 1,000 is the same as the distance between 1,000 and 2,000. That is related to how we perceive these changes in frequency. So we slice this up based on doubling. So one octave band is 1,000 to 2,000, and then 2,000 to 4,000. And then 1/3 is splitting that up into 3 parts. The business of and science of acoustical testing likes to split it up this way because it provides enough precision where we can make good engineering decisions, but not so much where this plot looks like a mess, if that makes sense, with huge spikes and dips everywhere.
And then one more, can you help explain what an NRC SAA value above 1.0 means?
It means that in the test, we observed more Sabins or more absorption area than there was area of material.
Okay. One more that we just got. You have already alluded to this, but are festooned baffle panels considered a flat object? Not just from a cost perspective. We run into conflicts with design teams about how many square feet of coverage we are providing regarding square footage of actual festooned baffles versus square footage of ceiling surface, which is less.
Okay, before I answer that one, are there any other questions? Because that's literally that's my next. Okay. So, okay, let me go into this topic, and then if I don't sufficiently answer your question, let me know. Okay, so we talked about the old-fashioned office with all the flat two-dimensional treatments, but architects and designers and product manufacturers are getting very creative. And part of it is to kind of sometimes to solve this problem. They took everything out. They wanted that hard look, and then, oh no, we made a mistake. Well, how can we reintroduce sound absorption? But now I'm finding I think people actually like the aesthetics of these sorts of treatments. And so we're talking about suspended three-dimensional objects. And for the scope of this presentation, I'm specifically referring to things that are installed in a regular, repeated array, like in these two examples. We have a problem, and many of you are already very well aware of the headaches and challenges. I will tell you, you're not alone. Every one of your competitors is dealing with the exact same challenge, which is to take the two-dimensional ratings and how are these applied to three-dimensional objects. So we define sound absorption coefficients, and therefore NRC and SAA, as Sabins per square feet. But what is the per square foot of this example of these baffles? We have 8 2-foot by 4-foot by 2-inch baffles. What's the area of these? And you might be thinking to yourself, well, obviously it's, but others might say, well, obviously it's something else. And that's where we're getting these wildly conflicting ratings from the same types of product. So the correct answer is that NRC is not applicable for that type of treatment. This NRC is not defined for this. ASTM does not define NRC for suspended objects. The correct way to present it is Sabins per object. Similarly, to demystify it a bit, it's like price. So what would be the cost per square foot for these baffles? You would probably push back and say it's the cost per object. We would sell those in the cost per object. But what if we tried to literally answer that question? What is the cost per square foot for example, theater seats? What's the cost per square foot for the owner of this auditorium to put theater seats in? And they demanded to know that from the theater seat supplier. Well, you could say, so you'd take a step back and you'd say, well, we know what the cost per chair is. That's easy. That's everybody agrees on what the cost per chair is. We can determine that. But cost per square foot, well, I guess the seat has it is three-dimensional, but three-dimensional objects do have a surface area, so we could pull up the CAD model for this chair and extract the surface area of the chair on all of its different surfaces and faces. So you divide the cost per chair by that surface area. There you go. That's your cost per square foot. That's the literal answer to what they've asked, but it's completely useless to them. Another one, you might say, well, that number looks really low because there's so much surface area here. What if we just made it the area of the cushion? Because that's all, you sit on the chair, you sit on the cushion, that's the function of the chair, therefore you only use that area. So you would get a different cost per square foot based on a smaller area, and that would be a much higher cost. Well, that would be a problem. But then there's a third way, which is to say, well, with a known spacing, there is an area of floor surface, a two-dimensional surface that's covered by this an array of chairs, and we could actually figure out the cost of this quantity of chairs divided by the area it covers, and we could give them cost per square foot of floor surface. And actually the architect could use that value to make predictions about how much it's going to cost to put seating in each of their different areas and different auditoriums. It's the only one of the three that's actually useful for anything, and we have the same problem with spaced object arrays. So what is the Sabins per square foot for a spaced object array? Well, we know the Sabins. The standard already tells us how to determine the total Sabins from this set of 8 objects, and then we divide that by 8, and then we get Sabins per object. Everyone agrees on that. That's how the standard is defined. It makes sense. How do we accommodate this demand for Sabins per square foot? What's the per square foot? Well, the literal answer, literal interpretation, is each of these baffles has 8 faces to it. And maybe that square foot area is the sum of all 8 of those faces. Truly, those are all exposed to the sound field, so maybe that's our absorption per square foot. Another would be to say, well, no, these are 2 foot by 4 foot baffles. So I know because I bought 8 square feet of insulation to make them, make each of them. So we should use that. We should use 8 square feet of area and take the total absorption per baffle divided by 8. That right there, that example is how you're seeing NRCs of like 1.6, 1.3 for acoustic baffles. Another would be what we are advocating, but we provide all of these calculations in every test report currently, since it's currently undefined. But we are advocating for number 4. We believe ASTM should standardize number 4. And the committee is working in that direction at ASTM, and it's starting to become more widely accepted. And that the area, similar to those theater seats, the area attributed to this object array is this here. It's the width of the array plus the space between, or the length of the array plus the space between, times the width of the array plus the space between. And what you get is an area of ceiling where the area per baffle remains the same regardless of the quantity of baffles. So the area per baffle of ceiling would be the same whether we had 8, 16, 32, 64, on and on. So we have this area of ceiling attributed to the set of objects. Right now, with it being undefined for these categories of products, the value of S matters quite a bit. So these are the same tests, the same exact raw data, the same Sabins, divided by the 4 different areas, which are possible ways to calculate this absorption per square foot value. And you see that it matters a lot. So if you use this 1 face per baffle method, you get a huge coefficient value. And what that turns into is that your apparent NRC, based on these different methods, is very different. So if we use the total exposed surface area method, so absorption per square foot of total exposed surface area, your apparent NRC is 0.7. If you use the area of 1 face per baffle, your apparent NRC is 1.6. And 3, if you use this continuous projected ceiling area, your apparent NRC is 0.95, which, by the way, is probably pretty similar to the effect of having this endless array of baffles in the room is probably similar to having a 0.95 acoustical ceiling tile. So even though it's a frustrating question to be demanded to know the absorption per square foot for suspended objects, this is the closest to actually answering what we think the architects are actually asking for when they ask you, what's your NRC? Any questions there? This might be a good place for questions.
Yeah, we do have one. How do you recommend the optimal spacing between baffles?
Mm-hmm. So, okay, good question. Perfect place for this question. So, the space between the baffles will make a difference in the absorption rates of the baffles. It will actually make a difference in the absorption rate in the baffle in terms of absorption per object. So as you increase the space between objects, up to a point, you will see more Sabins per object because they have a more efficient exposure to the sound field. That makes sense? Similar to light, right? If you had only 4 light bulbs in a room, you would probably better light the room by spreading them apart than you would by having them all together. Even if you're putting the same quantity of light in the room, if that makes sense. So as we expand the space between objects, we get better exposure per object. You'll see more Sabins per object. Also, if you know you are only going to be able to afford 8 baffles, and assuming a diffuse sound field, you'll be the most effective in installing them spread out. But that's assuming a diffuse sound field and assuming that you don't have any specular reflection problems. So that's that. But in terms of apparent NRC, the absorption per area of ceiling, you actually will have more apparent NRC, as we want it defined, if the objects are spaced closely together. This is because you have more fuzz, more sound absorbing material per square foot of ceiling. So you have a dilemma here, right? Now, the factors that will affect the performance of these baffles are many and have just expanded. So you have the fabric, the core material, the shape, the size, and the spacing. All of those are factors that affect the performance of this. Because we're dealing with a 3-dimensional array, this shape and spacing affects its performance. And this is true whether we do the apparent NRC thing or whether we don't and we still have Sabins per object. Now, the standard has a default ASTM E795, which is the mounting method standard, has a default type J, which is 8 baffles, 2 foot by 4 foot, 30 inches on center in the between rows, and 12 inches between objects in a row. So that is the default by the standard, but the standard says anything can be tested. You're not limited to that. We just have to document what it is. And that is a challenge. So your performance will vary based on spacing. What spacing do you test at? When my customers ask me that, I usually push it back to them and say, well, what do you typically install these at? And if in an example, these examples we've shown, this kind of gives a good illustration of this really should be tested at this space, and this should be tested at this space. But obviously that creates a lot of possible iterations, and you may want to think about standardizing to something like 30 inches on center or 24 inches on center, depending on your typical installation. If you find that your typical installation is very wide spacing, then you may want to just abandon the apparent NRC approach and only report and publish your Sabins per object and use a wide spacing. That's another possible. That's what ASTM historically has wanted you to do.
We have another one. How about the width of the baffle, since you don't have the area of the baffle?
Yeah, so the width, yeah, so the width of the baffle will affect it. And think of it this way, the Sabins per object will be different for a wider baffle or a taller baffle or a thicker baffle. They'll increase because you have more fuzz in that object. You have more sound absorbing material in that object. So yeah, the object size, and I know many of you sell many different sizes of objects, and that can be a challenge. So you may have certain sizes that are acoustically rated. I would use that term. If I didn't quite answer your question, follow up in the chat.
All right, another one just came in. How feasible is it to model with different spacing options with enough real test data?
So email me, and there's a paper that I have that someone tried to do a physical model of predicting the performance of baffles, but these are all based on the 2 foot by 4 foot size. And it's wonderful that many of you are coming up with very creative, clever designs, but they're all like different materials, different thicknesses. It's kind of gone way out of the realm of where those models made sense. And I think you're in the range of where the empirical testing is going to be way more effective than trying to do any kind of analytical model. Good news is these tests are not extremely expensive, and most of the time we can turn them around pretty quickly.
We do have another question. Which is higher, taller but fewer baffles, or shorter but more baffles if both scenarios had the same total square foot?
That's a good question. So the area of the area of material, but let's say we're going to use the two-dimensional area of the baffles, and you have the same square foot area of baffles, but you have that divided among more baffles in one scenario and that area divided among fewer baffles in another. I think, well, your Sabins per object will be smaller with the smaller baffles, but you may see more total Sabins with the smaller baffles spread over a larger area. It's a good question. I say that with like 70% confidence. So one thing we're doing at ASTM, and as I say this, I happen to be the current chair of the ASTM E33 committee. We're looking at this question, and we've been arguing and debating for a few years. It's been heated at times, and it's moving towards decision day on this possible method of giving you a single number rating for absorption per square foot for a set of objects. And that's as it is shown here. I will tell you, this isn't a different test. This is the exact same test. And this calculation, if it's ever standardized, this calculation could be applied to old tests. So you would not need to retest anything. We could do a revision and do a new appendix. It's also a coin toss if it'll ever pass. If many of you are on ASTM, you'll know can be a conservative organization.
What literature is available to support the test design? I recently heard that Leo Baranek and Paul, not even going to try to pronounce that last name, debated this topic.
Yeah, I think it might be Paul Sabin. So there was there.
It starts with a V. It's Veneklasson.
Oh, Veneklasson, Paul. Yeah. So yep, no, we still argue and debate about a lot of the things that we've discussed today. What I'll say is the Sabin as a unit of absorption, pretty much everybody agrees that with this test as a way to test materials for comparison purposes, for their ability to reduce reverberation in an enclosed space, everyone at ASTM is on the same page there, that the Sabin is the right unit, and this reverb chamber method is a good test method. Where we get into the controversial side of things is when we try to do this forbidden thing of taking a set of objects and turning it into absorption per square foot. That's where it's controversial. And it's not a test. We're not changing the test. We're changing the way we present data. Now, currently, Riverbank will present all of these. We will provide Sabins per object, provide total absorption added, and we'll provide all of these three different ways of calculating this. And then we leave that to the acousticians and acoustical engineers to think about this and digest it and use the values that are useful to them.
All right, one more question. For a single number rating, why not just average Sabins per object at 250, 500, 1,000, and 2,000?
Yep, yeah, I would agree with that. So I think that's a possible way as a product manufacturer that you could present your results. So that's a good segue here to my next slide, was what should manufacturers do? So I've defined the challenges here, or the confusion, the complexity. Well, what do we recommend you do? So first, so we have some customers, we love them, and they will test many iterations of size and spacing. And we're thankful for that. But we also recognize that some manufacturers don't have that kind of budget. And I would start with, your most common sold products, or where you're getting requests for absorption performance the most frequently, and identify those as acoustically rated. One of the good things about this test, so we said the bad thing is the test can be very specific to the configuration, but the flip side, the good side, is the test lasts forever. It doesn't expire, and you can add to your catalog of acoustical test data every year. And actually many of our customers do that. They'll pick out a few different examples or products every year and just keep adding and keep using that data. So start with ones you want to identify as acoustically rated. And then here's how we think you should present your results. So these are our Riverbank yellow baffles. So don't worry, we're not trying to compete with you. These are hideous anyway. So they're the Riverbank yellow baffles. They're up to 16.94 Sabins per baffle at 1,000 hertz. And click here to download the test report. So we would love it if you put our website up and made it available for people to download. We'll work with you on what product information we present. So if you're concerned there's something proprietary, which often there is not, we can not describe that so that you can make the full report available. But either identifying the Sabins at 1,000 hertz or doing exactly like the commenter suggested, is taking that 4-frequency average of 250, 500, 1K, and 2K and averaging that, and then saying average Sabins per baffle of 16. That's probably the technically most correct way to do it. The problem is nobody knows what to do with that. I mean, I should say acousticians, acoustical consultants and engineers, they'll know what to do with that, but they actually want the whole test report. They want that whole, acousticians want this whole spectrum. If they can get their hands on it, they want it. And that 4-frequency average is not super useful to them for modeling, although it might give them a good rough order of magnitude for general use spaces. So that would be the most correct. And then if you're going to do it, if you're going to do a non-standard NRC, make sure that you're saying that it's non-standard or it's not official. We like this, like a parent NRC. You could use that. A parent NRC of 0.95 with 8 baffles per 100 square foot of ceiling area. So that is this right here. And this will be in our report. That's the absorption per square feet of ceiling. So if you provided all 3 of those for your acoustic baffles, you will look like a leader in the industry. You'll give the acousticians and the acoustical engineers what they're looking for, which is that spectrum data, and you'll give the architects what they're looking for, which is that relative comparison to the NRC that they're used to seeing for ceiling tiles. Because whether they know it or not, and whether you know it or not, what they're really asking for when they ask you for that parent NRC, or what they ask you for that NRC is, how does this compare to a continuous flat installation of ceiling tiles? And this is the only method that answers that question. All right, that's the presentation. Any further questions?
Yeah, we have another question. As an acoustical engineer, how do I use a test report with Sabins only and extract an apparent NRC to compare to a traditional NRC rated product, i.e. comparing a felt blade baffle to a ceiling tile? I'd like to compare over the traditional octave band spectrum.
Okay, good question. So all of our test reports will have on the last 2 pages of a type J or a spaced object test, we will provide this calculation for you. So we'll provide the Sabins per square foot of ceiling, and if your spacing of those baffles is intended to be the same as the installed spacing, you could actually use this as a sound absorption coefficient in your model by making a horizontal plane with that value. If the spacing of the baffles as you plan to install them is different, this value will be different, but also the Sabins per object will be different. Then you have to go back to using something, or basically using what a lot of acoustical consultants did historically, is take this equation and solve for A. You know the volume of that specific room you're working in. You either have tested or modeled the existing reverb time, and you have a target reverb time. And the change in A is what you'll need to get from your existing to your target. So basically a little bit of algebra, and you can solve for how much additional Sabins of absorption you'll need to get to your target reverb time. And the test result will give you the Sabins per object. So you divide the additional Sabins needed to get to your target reverb time by the quantity of object, or by the Sabins per object, and that will give you your quantity.
All right. Is it appropriate to utilize the newer 3D apparent NRC calculation for festooned horizontal baffles, as opposed to treating them as a flat installed panel, given that they are curved and technically have more surface area than the roof area they are covering?
Yeah, that's a good question. So one thing we have kind of figured out or determined, and this is one of the reasons ASTM is moving so slowly on this question, is because there are certain types of products where this makes a lot of sense. And then there's some shapes where it's not obvious that it does. So ASTM will always have both. In fact, this Sabins per area of ceiling, if this passes, will always just be an optional alternative, or optional in addition, I should say. So you'll always get the Sabins per object, but you may also, in certain circumstances, get the Sabins per square foot of ceiling area covered. But as time goes on, we will add additional items to this Appendix X2 in C423 to accommodate things like you just mentioned, the catenary banners, or actually one I would like to tackle next would be theater seats, which isn't as simple as you might think. There's some complexity in how they overlap each other, so that might be need to determine. But over time, we would add additional absorption per unit area calculations to the standard.
So I'm going to ask, so in this baffle example, what would happen to the absorption if the baffles were rotated 90 degrees and became flat?
Great question. So the Sabins per object would increase, because I think that same kind of topic we talked about before, how they become more efficient absorbers the further away they are from each other. They per object, you get a better sampling of the sound field. They shadow each other less. That makes sense. But then the Sabins per square foot might drop, actually, depending on the spacing. So if you had a relatively tight spacing and we were using the Sabins per square foot of ceiling, you would have more fuzz per square foot of ceiling with vertical baffles relatively close together than you would with flat baffles. So it's, yeah, the shape of the installed array does significantly affect its absorption. And this is one of the pushbacks we've got from trying to do this absorption per square foot for baffles, is just how critical that spacing is. But it's critical even with Sabins per object.
Okay. This is kind of a long one. Just as an aside, do designers apply an apparent NRC rating to audience or patron clothing as represented by a percentage sold crowd, as their presence will affect the acoustic absorptive design of a theater or arena? Obviously, this is something that can't be isolated and empirically tested, but is something that affects real world acoustics in a venue.
Yeah.
Good question.
Yeah. So yeah, I guess it is related. Spaced objects, theater seats would count as a spaced object, right? So we test these at our lab, and manufacturers will often have us do it in unoccupied and occupied conditions. And in the occupied conditions, the selection of people is pseudo-random. It's just who we can find willing to sit. And some of those people are more absorptive than others. And in the summer, they may be a little less absorptive than they are in the winter. And so there's some uncertainty that comes from that. But that uncertainty in acoustical modeling is something acousticians are very good at dealing with. They understand that uncertainty, and they kind of account for it in their model as they become experienced modelers. But yeah, you're right. The different clothing can affect things. The different hairstyles, potentially too.
All right, I don't think we have any other questions coming in.